minimum by inspection. Let's call it by inspection. All right. So pretty much it's everything we'll learn back in Calculus 1, it's going to work the same. Yes?
Are we always finding extrema in regards to the z-axis?
Yes. Yeah, because that'll be the z value, which is, well, that's going to be either the positive or, well, the max or the min or something new that we're going to learn here. So in Calc 1, we got maximums and minimums. However, in 3D surfaces, well, we're going to learn about new kinds of points. So we will have three possibilities. Number one, we may have maximums, we may have a minimum, or we may have a saddle point. It's kind of a weird point. Well, actually, we talked about saddle points earlier when we looked at the quadric surface at the beginning of the semester. And well, here these two, well, those two represent a maximum right there at the top of the hill. However, check this point in the middle. And if we observe two trajectories to get to that point, what do I mean by that? Well, so if we get to that point in the x direction, doesn't that look like a max in the x direction? I know there's some weird perspective in there. However, if we approach that point in the y direction, it's a min. So it's a maximum and a minimum at the same time, right? So that's what we call a saddle point. Well, because it looks like those saddles to ride those horses, you know. Another way to relate these saddle points, we already mentioned the Pringles chips, right? If you look at the middle of the Pringles chip, they have their maximums and minimums at the same time, depending on the direction you look at the very middle of the chips. And well, so how are we going to find these maximums and minimums for functions of multiple variables? So, all right, so we're going to use the second partial derivative test, which is also known as the Big D test. That's because of the quantity that we evaluate, which involves finding a few partial derivatives. And well, so the condition is that all the second partial derivatives of the given functions are continuous at the given points. Okay, and center at those critical values, and for this second partial derivatives, it's the partial derivative twice with respect x, twice with respect y, and also the mixed partials with respect x and then respect y, or the reverse. Recall that we looked at the fact that regardless of the order you do these two derivatives, we always get the same result. All right, so let's see. So let's look at the conditions. So back when we used the second derivative test for functions of single variable, if the second derivative is greater than 0, then minimum, because at that given point, so let's call it C, C1, C2 for critical values. So in this case, it's positive, so we have a happy face, you know, we have a concave up. And if the second derivative is negative, we have a maximum. That's because, well, sad face, but it means maximum, right? It means concave down, gives it the max. Well, the conditions for the D test here are a little bit more complex, more elaborate, but well, so actually when we do this in practice, well, all we need to have is this idea, these few ideas down. So what about them? Well, so if we compute this quantity D at the given at all the critical values, that is, it's a second partial derivative evaluated at that critical point with the both partial derivatives with respect x and respect y, minus the mixed partial squared also evaluated at those given critical values. So we need to make sure that both the d quantity and the second partial are both positive, then we have a relative minimum. Do you see the relation? How, well, second derivative is positive, minimum, it's again like the concavity test. And in the case that, well, the quantity d is positive, but the second partial is negative, well, we have a relative maximum. In the case in which the quantity d is negative, we call it a saddle point. And the test is inconclusive when d equals to 0. Right? In the same way that we did for functions of one variable. All right, let's use the second partial derivative test to prove that the function that we just did in the previous page indeed has a minimum at 1, 3, 4. All right, so let's take the partials again. Fx, well, I'm just going to use the results from the previous example. X minus 1, Fy equals to y minus 3. But in this case, we need the second derivative with respect x. Well, the derivative of 2x will be 2. The second partial with respect y, that's the derivative of 2y, and that's also a 2. And the derivative of the partial derivative with respect x first, which is 2x minus 2, and then we do that derivative now with respect y. What is that going to be? 0, right? Because that first derivative with respect to x doesn't contain any y, so it's constant. The derivative of a constant is 0. So let's find the critical value was, or the critical point is 1, 3. So let's evaluate the expression d at ab. In this case, that's f double partial with respect x at a comma b times the second partial with respect y, both, and in this case minus the second partial with number 1, the mixed partial rather, quantity squared. Okay, well, so in this case, notice our second partial derivatives are constants. We are not going to have any values of x and y to plug in 1 and 3. So this is 2 times 2 minus 0 squared. And in this case, d, well, actually this is 4 first. Okay, so this is equal to 4. So what do we have? Let's put the two results together. Number 1. D in this case is positive 4, that is d is greater than 0, and f xx, what's the sign of f xx? Isn't it also positive? Well, looking at the definition above, what is that going to mean? It's a minimum, right? We have both positive, the d quantity and the second partial with respect x. So this means indeed minimum. All right, let's have a look at another example. Consider the function z equals f of x, y equals to negative 3e to the negative x squared plus y squared. Find all relative extrema and saddle points whenever appropriate, right? So we can get all of them, some of them, or maybe nothing. So let's see. Fx partial with respect x will be, well, so that's negative. Okay, it's going to be itself the exponential e to the negative x squared plus y squared, and by chain rule we need to multiply by the derivative of negative x squared, which is negative 2x. But that negative 2x multiplied with negative 3, isn't that going to give us a 6x? All right. And same for the partial derivative with respect to y. So we're going to multiply the derivative of y squared, but notice the negative sign. So that's going to be the derivative of negative y squared, which is negative 2y, times the negative 3 here. It's going to give us a 6y e to the negative x squared plus y squared. All right, so from here let's set the partial derivatives equal to 0. In other words, we will set 6x. Well, actually, let me just write down equal to 0, equal to 0. Well, in this case, we can use the zero product property. That means, so this equation equals to 0 if, for the first case, either 6x or e to the negative x squared plus y squared are equal to 0. Well, in this case, 6x equals to 0. That's just for x equals to 0. But what about the exponential? Recall, exponentials do not go to 0, right? So just cross it. All right. And on the next case, that's going to be a 6y equals to 0. And well, I don't need to set the exponential again because we already did it for the previous example. For the previous step. So there's only one critical value, and whenever we want to test these critical values, well, I'm gonna make a table. Well, actually, after we get the second partial derivatives. Well, all right. So in this case, for the second partial derivatives, notice how we have to use the product rule. All right. So, okay. So using the product rule, that's the derivative of 6x, which is 6. Times the exponential plus the derivative of the exponential, which is itself. That's actually e to the negative x squared plus y squared. And using chain rule, the derivative of 2x of x squared is 2x. All right. And that's 2x. Well, let me have a 2x over here, but times the 6x. This will become 6 e to the negative x squared plus y squared plus 12 x squared e to the negative x squared plus y squared. So that's the second derivative with respect to x. Let's do the same for the second partial with respect to y. So doing the same, well, it's actually gonna be the same format, but in this case with a y squared. Well, let me do the whole thing anyway. So that's going to be the derivative of 6y is 6 times the other factor, which is e to the negative x squared plus y squared, plus e to the negative x squared plus y squared times the derivative of, oh, actually this is supposed to be negative. Here we change this to negative, times negative 2y times the quantity u, which is 2 or 6y. All right, and that reduces to 6 e to the negative x squared plus y squared plus minus 12y squared e to the negative x squared plus y squared. And so we are going to need one more partial derivative. That is going to be the mixed partial derivative. All right, for the mixed partial derivative, that's going to be f x and y. So that's going to be the derivative with respect to x, but this time we're going to differentiate it with respect to y. That is the 6x e to the negative x squared plus y squared times, by chain rule, the derivative of negative y squared, which is negative 2y. And this one reduces to negative 12xy e to the x, or rather negative x squared plus y squared. All right. Okay, let me box these second partials. So that's the first, second partial. That's another one. Oops. And that's the third one. All right. So technically what we have to do is create the big D expression, which is in this case f double x times f double y minus fxy quantity squared. Well, but think about the expression that it's going to look like when I put these two together to multiply. Did you see how big it's going to look like? Well, I don't want to do that. I think we can do the calculations by just looking at the function. So in this case, we're going to make a table. And that table is for the critical values, and we're going to get the calculations on the table. And for fxx, fx or fyy, and fxy. And in this case, for the critical values or critical points rather, the only critical point that we got in this case is 0, 0. So let's see, what do we get when we plug in 0, 0 on the second derivative? Well, for the first term, so e to the negative 0 squared plus 0 squared, isn't it a 0? So e to the 0 is 1. 1 times 6? 6. And for the second term, well, plug in a 0 here for x, the whole term is going to get zeroed out regardless of whatever e ends up being. What about f double y? Isn't that going to be also a 6? This, because of this y squared, plug in y equals to 0, that's going to get zeroed out. 0 squared plus 0 squared, it's still 0. E to the 0 is 1 times 6 is 6. And well, plugging 0 for x and y here, that's going to be 0. Alright, so let's compute the quantity d in this case. So d will be 6 times 6 minus 0 squared, which is in this case 36. Alright? Now, we also need to calculate, we don't need to calculate. Actually, we need to just go back and refer to the values. And it's better to have these values in a table here instead of coming back to the second partial derivative with respect x to check if it's positive or negative, because we already have it here. So in this case, d is greater than 0. So now we need to check whether the second partial with respect x equals is positive or negative. So in this case, it's positive. All right. So what is that going to mean according to the second derivative test? Minimum. So we have a minimum in this case. All right. So let's see. I know all these partial derivatives just for one critical value. All right, let's have a look at another example. So what do we have? Something a little more interesting. And well, so consider the function f of x y equals xy minus 1/4 x to the 4th minus 1/4 y to the 4th. All right, let's find the usual relative extrema or saddle points, if any. Okay, so let's find the first partial with respect x. So for the first partial with respect x rather, that's going to be, okay, what's the derivative of the first term with respect x? Y, all right. And that's going to be plus 4/4, that's 1, that's x cubed. And that term is going to get zeroed out, right? Yes, negative. Mm-hmm. And f with respect to y, that's the derivative of the first term is x. The derivative of the second term is 0 because it's constant with respect to y, and minus y to the 4th power. All right. So in this case,
Y to the third.
yes, to the third. Yeah, to the third. And I have my notes here. All right, so let's find all the critical values, all the critical points before finding the second partial derivatives. Well, so number one, this we have to set this equal to 0. And in this case, this means y equals x cubed. And this means x equals to y cubed. So we need to solve this system of equations, of non-linear equations, more in particular. But for this one, we will have to do a pretty interesting substitution. So, in this case, let's see. How can we do this substitution? Well, so we can get an equation in terms of x. How about we substitute y equals x cubed over here? So, we're going to plug it in here. That's going to give us the following equation. That's going to become x equals to the quantity y, which happens to be x cubed, and then cubed that x cubed. That's going to be x equals to x to the 9th, and well, in this case, that's going to give us x minus x to the 9 equals to 0. And then from here, we can solve this equation by factoring, well, or we can reverse the order of the signs so we can also solve the equation and factor out 1x, and that's x to the 8th minus 1 equals to 0. Well, on the one hand, this means x equals to 0. This means x to the 8th power minus 1 equals to 0. Well, the first one, well, that's already one of the critical values, x equals to 0. For the next one, we will have to use the, well, not the square root property, but the 8th root property. So, x to the 8th equals to 1, and then we would need to find the 8th root on both sides. However, is this enough? Well, let's go back and review the solving equations involving radicals. Whenever we have like an equation, well, the square root of x, or rather x squared equals to 4, that means x equals plus or minus root of 4, which is plus or minus 2. That's when the power is even. However, when the power is odd, x to the 7th, for example, equals to 4, for example, so x, in this case, we don't need the plus or minus. That's the 7th root of 4. So whenever the exponent is an even exponent, this is where we need this plus or minus. And what's the 8th root of 1? Isn't it just 1? So plus or minus 1. Alright. Okay, so we already got these values of x that are going to be part of the critical values or the critical points. So let's list them. So critical points will be 0 comma something, -1 comma something, and 1 comma something. What are the y values? So what we can do in this case is go back to the y equation. Let me highlight it so you can see which one is it going to be, to get the y values corresponding to the x values that we just found right here. So 0 cubed, that's going to give us a 0. -1 cubed, what is that going to be? -1. And 1 cubed, that's going to be 1. All right. So let's see. Let's find the second partial derivative so we can create the table and find the d quantity which actually involves those second partials. So f second partial with respect x, well, in this case that's going to be -3x squared. F with respect y, that's -3y squared, and fxy, that is the derivative that we got with respect x first, do it with respect to y, the second term zeroes out, and the partial derivative is just 1. Alright, so we're ready to create the table here. So for this table, critical point fxx, fyy, fxy. Alright, so In this case, well, let's evaluate the second derivative at the point 0, 0. Well, what is this going to give us? Is it not a 0? And what about also 0 for the second partial with respect to y, and fxy? It's 1 for all three cases actually. Okay, so let's evaluate this for the second critical point. So at x equals -1, this is going to give us, well, -1 squared. That's positive 1 times -3 is -3. Same here is also -3. And it doesn't matter what we do in this case because we're squaring, whether we square positives or negative, this is also going to be -3 and -3. All right, let's find the d values so we can compare with the corresponding fxx. All right, so let's see. Okay, 0 squared plus 0 squared is not just 0 minus 1 squared. That's -1. And -3 squared, that's +9, plus -3 squared, that's also a +9. So that's 9 plus 9, which is 18. 18. Oh, wait a minute. No. What am I doing? No, I'm supposed to multiply, not to square them again. So -3 times -3 is +9 minus 1 is 8. And same here. Well, number one, let's look at the first critical point. For 0, 0, what do we have? We have d equals, well, d is a negative number. What's the result when the d value is a negative number?
The saddle.
Saddle point. What about the point -1, 1, and also 1, 1? In this case, because d is greater than 0 and fxx on both cases are less than 0, they're both negative numbers, right? For both critical values, well, positive d value but negative second derivative, so it's concave down basically, which means maximums. Okay.